Good morning to all the participants. This is K. Rajesh, Head of Civil Engineering Department, Vaageswari College of Engineering, Karimnagar. First of all, I thank all the participants for registering this FDP, that is Emerging Technologies in Civil Engineering and Application. It's been our pleasure to host all the participants of today's FDP session. I'm sure that the participant will benefited by attending this FDP. Let me give some introduction about our college. Actually, the society was established by an eminent and educated personalities in the name of Goddess Saraswati Devi, that is Sri Vaageswari Educational Society, during the year 2003. The Vaageswari College of Engineering was established in the year of 2005 under the leadership of General Secretary Dr. Gandra Srinivas Reddy Garu, who is a doctor in Ayurveda and a dedicated missionary and crusader in the field of education. He is the spirit and force behind this reputed organization. The Vaageswari Educational Society was established with a crystal vision to produce professional having scientific intellect, innovation, and imagination. About Civil Engineering Department, the Department of Civil Engineering at Vaageswari College of Engineering is producing high quality technical manpower needed to industry, R&D organization, as well as academic institution since 2013 with an intake of 60. Intake of 60. The intake has been increased to 120 in the year of 2014. Addition to UG program, we have diploma civil course with the intake of 60. The department has full-fledged laboratory, library, and infrastructure facilities. Many of our students are placed in reputed companies like L&T, GMR, Mail, Lanco, Navayuga, GVK, Aparna Infra, and many more. The academic activities of the civil department emphasize deep understanding of fundamental principles, development of creative ability to handle the challenge of civil engineering, and the analytical ability to solve problems which are interdisciplinary in nature. The department is actively involved in basic and applied research and consultancy, and also provide technical guidelines for the benefits of the students and entrepreneurs by organizing short-term courses, certificate-oriented training programs like BIM, Revit Architecture, StatPro, ArcGIS, MEP, etc. I thank all the coordinators and faculty members for giving me this opportunity to speak a few words about our institution. Thank you one and all. Now Prachi Madam will give the introduction about our today's eminent speaker. Madam, go ahead.
Okay, thank you, sir. Hello and good morning, everyone. I'm Dr. Prachi Singh, coordinator of this 5-day online FTP. For this program, we got an enormous response, and for which we are thankful to our eminent speakers who are ready to spare time from their busy schedule to deliver these lectures. Today is the first day of the program, and I would be glad to introduce our today's speaker, Dr. Prabhakar Shukla. Dr. Shukla is currently working as hub scientist at the Department of Civil Engineering, IIT Delhi. He has published numerous research papers, technical notes, book chapters, books in the reputed journals. So, Dr. Shukla is also a member of editorial board of several SCI and Scopus journals. His research interest includes hydrological modeling, climate change, water resources management, and GIS applications. Today, Dr. Shukla is going to introduce us to concepts of modeling of groundwater system. So with that note, I would not take much of your time and would like to request Dr. Prabhakar Shukla to spread the knowledge with all of us. Thank you. Prabhakar sir?
Yeah, thank you, Professor Singh and Head of Department, Vaageswari College, for giving me this opportunity to make the introduction of this very vital topic to the general audience. And I also congratulate the institute and the coordinators of this course for having thought process of having webinar on this very, you know, uh, very important topic to all of us. So without taking much time, I'm coming straight forward to the uh, topic. And I'm assuming that the participants, those who are attending, they have some basic knowledge of the water resources management as well as the groundwater system. So basically, today I'll be talking about the concepts and the modeling of the system. In the concepts part, I'll be talking about mainly the hydrological system, how the water occurs, how it returns to the earth, what are the different phenomena involved. Then I'll be talking about the components of the groundwater specifically, the aquifer system, how the groundwater flows, what is the age of water and how do we identify that, what are the different dynamics of the groundwater system, and then we'll move to the systems approach, what are the different approaches we should have and what we can, how we can like contribute in the terms of research or understanding of the complex system. And then we'll look forward some challenges which are associated in terms of different perspectives. Then we'll move to the model development. We'll see what are the basic requirements for developing a groundwater model or any hydrological model. We'll look forward for the different frameworks which are associated with this, and I'll give you an example for a conceptual model, and then I'll present a case study of the groundwater modeling in the Indo-Gangetic alluvial plains, and in the end I will give you idea about and I leave all the participants with a thought process how they can proceed for the research or their ongoing BTech projects, masters or the PhD with respect to this groundwater modeling system. So I'll start with this variable resource of water because it's very easily available. Sometimes maybe beneath the aquifer, not easily, but its availability, I'll rather say, its quality and the minimal requirements for storage, and also the transmission infrastructure. For example, if we are depending on the surface water, we need to take the water to some treatment plant. We have to have some mechanisms for the pumping, and we have to invest some money in terms of the energy. So overall, if we look at in comparison to the groundwater, simply you can have a pump, you can withdraw the water and you can use without even treatment. So its availability and the quality has created a stress on this resource. And the diagram which you all are, you can see on the screen, I hope you all are familiar with this. It's a basic hydrological cycle. Like we can see groundwater is derived almost entirely from the precipitation. And it is the portion of the precipitation, example, for example, if you see in the other regions, it's not only the rain, it's also the melting snow. And it moves from the upland parts of land and goes into the soil. And by the infiltration process, then again it goes into the ground. And thus there is a circulation of the whole system. And of the water that falls on the land surface, only 25% of it get enters into the groundwater system, or it percolates through the soil and goes to the system or contribute in different parts. So the direct surface runoff is a portion of the precipitation or the rainfall that has not gone underground, but it runs over the surface as a stream. And when we talk about the total runoff, not only the surface runoff, the total runoff, then it includes both the groundwater discharges into stream, maintaining their base flow and all these things. So likewise, we can see that there is one more component called evapotranspiration. That means when the water being get close to the environment from the groundwater itself, this in terms gets so much water is being means gained and lose during this process. For example, in summers we can see that there is a decline in the water table. Generally, we say that the one who is declining, the main reason behind the decline is that extraction of groundwater. But there are other forces like evapotranspiration as well. But there are so many different things to talk about. I'm not going much into it. And for this reason, much of the groundwater recharge for the year takes place during the fall and the winter months, because because the gaining season is during the monsoon only. In India, we are depending on that. Next, I'll be talking in the last term view, where you can see there is a red arrows you can see in this. So the in the part where I have highlighted, there are two different directions. So I'll be talking more about the direction of the groundwater flow in the upcoming slides. But the generally groundwater flow follows a descending surface topology and surface water flow. Example, groundwater typically recharges in the upland region and discharges into the stream where there is a, you can say, valley or the cone of the valley in the low-lying portion of the watershed. So I'll be talking more about this in the upcoming slides. And also there are seasonal fluctuations, the third factor which have effect on this whole hydrological cycle. That is, the surface water elevation may cause transient change in the relation between the groundwater and the surface water. For example, if in summers and winters we can see the effect of the changes in the temperature alters the soil moisture, and also the water demand by the general public, maybe for the domestic or horticulture use. So in the both ways, the seasonal demand is giving a transient effect on this. So temporarily elevated surface water elevation, for instance, may cause a stream to maybe gaining in throughout, not throughout, but for the some period of time. So likewise, this is the whole hydrological cycle which I was talking about. Now I'll be shifting to this groundwater resources. And in India, we divide the groundwater resources into two main parts. One is dynamic, which is also known as replenishable, and second is static or the in situ. So the dynamic component, which is the first, is measured as a flow in meter cube per second. That means the dynamic component is an annual recharge of the aquifers, while when we talk about the static resource, it is the groundwater volume available at the depth of rock formation. That means it has been stored over the 100 or the 1,000 years. In India, like if you heard about the CGWB, Central Groundwater Board, so India is one of the few countries engaged in the detailed assessment of the dynamic component at the regular interval since 2005. And from 2009 onwards, they have estimation made at every 2 years. If I'm not wrong, the latest is 2017 and the 2019. These are in open source. Anybody can see the total groundwater availability in the area. It's district-wise and the basin-wise detail is also available. And there is no firm or the detailed policy on the static water resource conservation, its rejuvenation, its use. We have a general understanding that we must restrict the extraction within the dynamic resource available in that particular area. So the static component should be used in a case of emergency like drought, and in fact, overexploited areas where there is an incremental eating up of this static resource, there is a resulting like you can say drought in that particular region, or there is a permanent damage. For example, if you can see or you can recall the Africa and then Chennai itself in the last few months, you have seen the permanent damage to the aquifers. Even after the rainfall, they were unable to recover of this damage. So preliminary assessment shows that substantial static resource in alluvial areas and not so much in hard rock aquifers because of its inherent aquifer properties when we see about the porosity or the hydraulic conductivity. And therefore we need to have effort to access the static resource in the countrywide, and we should look forward for a firm policy on the extent of spatial and the time domain use of this static resource and its rejuvenation in various topology and agroclimatic zones. And when we come to the storage of the water, we have two different reservoir systems. And groundwater reservoir is we call it confined or artesian aquifer if it is sandwiched between two impervious zones or confining units, like you can see in the figure. And the unconfined aquifer is also known as the water table aquifer. It is the uppermost saturated layer, and the surface of the water table is open to the atmosphere. That means at the water table there is an atmospheric pressure working on it. This is the major difference between the confined and the unconfined aquifer. And in confined aquifer, the water level in a well rises above the top of the aquifer. So the potentiometric surface is the level to which the groundwater would raise in a well completed in an aquifer. So if the water level rises above the land surface such that the water flows from an open well to the well is called this is artesian well. And now if in this figure in the bottom you can see there are two wells A and B which are shown there. So well A penetrates in the unconfined aquifer and its water level reflects the water table, which is very clearly visible in figure A. And if you look at the well B, it penetrates to the confined aquifer and it is flowing because the potentiometric surface is above the land surface. So this is the basic aquifer, and there are so many different categories under this. So I'm not going much into that, just a brief idea. Next question is how groundwater flows. There are surface water which is flowing in the open atmosphere. We can see them, we can visualize, and so we can try to give our views about their quality, their quantity, just by visualizing the effect. But the groundwater is a tricky and a very complex phenomena. So the water which infiltrates below the ground and recharges the groundwater in the areas where the permeable deposits are there. So today, if you see the urbanization, we have converted all the permeable areas into the concrete ones. So that's the reason the surface runoff is increasing, and the whatever rainfall is there, it get converted into the surface runoff, and there is a lot of flooding. And we say that the area is flooding because there is inadequate infrastructure, while we are also responsible for this. So you can see that the groundwater, the rate of the groundwater flow and the amount of water that can move through the formation depends mainly upon its porosity and how well the pores are connected. These are two very important parameters for the movement of the groundwater. For example, if you can see in this figure 1 on the top, you can see that the large amount of water moved rapidly through formation which are large connected pores. For example, the gravel, they have very rapid, you can say, the movement of water. And and also the bedrocks which have high fractures, they have very good movement of the water. Water moves slowly through the formation with the small or the poorly connected pores. For example, the clay. If you have seen the water drop on the clay, then you can see that it's a very slow formation, very poorly connected pores are there. So the movement is very slow. And then we have formation that allow the large amount of water to flow, such as the sand and the gravel. So in contrast, clay, silt, and granite formations are much less permeable overall. But the exact path that the water flows along can be a very much complex. Most of water will take the path of least resistance or the flowing through most permeable formations. So some recharged water can also flow downward through unconfined aquifer to recharge the deeper confined aquifers. And eventually it flows to discharge location that are several kilometers away, as you can see, where there are two lines and in between there is a discharge area. Next is the age of groundwater. So every human being has an intuitive understanding of word age. So even if you ask a 4-year-old child, you will perhaps not get a direct answer, but it will probably raise 4 fingers before hiding behind her or his mother's legs. So this demonstrate that we are aware of meaning of age in a very early childhood. So every human being knows that the age, by definition, by the means of the time difference between the moment of the birth and the moment at which the question is asked. So it's very simple. But when we talk about the groundwater, it's when we talk about the groundwater, it's like hard to visualize. And first is we have categorized in two different ways. First is idealized groundwater age, and second is tracer age. There are theories about the young water and the old groundwater. So I'll be coming that to later. I'll talk about the idealized and the tracer age first. Idealized groundwater, it assumes that there is a water parcel that moves along the flow path without mixture from the recharge area to the sampling point. Now, this definition sounds straightforward, but it bears a terrible problem. Whereas the humans, we have a, like, we can divide in different parts. We can have a individual or as a parcel or a group of people. We can count that. We can count and we can identify or we can arrange that. But in case of groundwater, there is no such individual parcel which exists. So one way to get out of this problem is to simply idealize the thing. That's why we call it idealized groundwater edge. So what we do in this, we use our own imagination. We create infinite small water parcel within which exist only in our mind. We assume no or process like mixing, dispersion, or diffusion, which influence these water parcels. And to this small water parcel, we attribute a flow path and the time difference needed to travel from the groundwater surface to the point of sampling. And of course, this is not very realistic, but um, there is a like assumption, and we have to have some ideal condition, and we have to find out. But when we come in the real field, or we are doing the modeling, and this will create a lot of uncertainties in this. So there is one way to there is no other like known method to determine the idealized groundwater age. So we have no experimental techniques so far using that. So one way to come out of this or to solve this, we have to follow the tracer age. Tracer is like a isotope or any other component which will add to the starting point. Like you can see in this figure, where the black point starts and the arrow starts, there is a graph. You can see how much time it takes to travel to other point, and likewise we can try to find out the difference between these two, and we can have some idea about the like age of the water, how it's moving, and how what is going to do. Now the question is how you are going to do that. What is the mechanism behind that? So there are two different terms in the tracer age. One is young groundwater, and second is old groundwater. So in young groundwater, we refer to the different isotopes and the chemicals which were introduced since 1950s, because we assume that so many of atomic parts and all these other substances, they were introduced in our climate and in the environment of since 1950 itself. And before that, we consider it as a old groundwater. But the new groundwater age is much more suspected to the pollution, because the old is around maybe thousands year old, which is stored there, and there is no interference of the contamination we assume. So this is the brief idea about the aging of the groundwater. Now we'll be talking about the dynamics of the groundwater. So this is a stellar diagram which shows that it's a very dynamic field. And if you start with the center of the figure, there is a groundwater volume. If you can identify, there are two different components, inflow and outflow. So these are the two major components which affect the groundwater dynamic. So the groundwater volume fluctuation depend upon the rainfall, the sewage water, the surface water percolation, which I have talked in the first slide. Then we have recharge, which can be artificial, which can be natural. Naturals are now like they have been out of scope, because so many of people have already diminish their quality, somehow encroachment over this. So we are moving for the artificial recharge. And then we also have the surface flows which enter into the aquifer to balance the system. In addition, if you see, we are withdrawing water for the crop and moisture which is there in soil, obviously, because if the soil is saturated, the whole rainfall will convert into the surface runoff and it will not interact with the water. We have evapotranspiration, which I have explained in the first slide. We have surface outflows, and the subsurface outflows are there, which are gaining and the losing streams there. And we have groundwater extraction outflow from the other side. So in this, the extraction of groundwater for agriculture activities is a major, like you can withdraw in Indian context. We are highly depending on the groundwater for our agricultural activities. And so it's a major focus, and we can determine the farmer's economical behavior, and indirectly, which depends on the farmer's net income in any particular area. It's a very general statement, and clearly from farmers' economic behavior, it's very sensitive to somewhat related to the economic policy and the instruments, including the different designated uses and the water demand and pricing policies as well. So with this implementation of economic policy and the instruments in the agricultural sector, and we expect that the farmer will respond to the policies by changing their cropping pattern and the production technologies, which is not in practical in Indian scenarios. So logically, by agricultural sector adaptation to the economic policies, the exploitation of the aquifer in the groundwater system and its volume fluctuation will be compatible. So we need to have so many of dynamics to be involved while framing a policy in terms of economic, socio-economic, hydrology, hydraulics, and the complexity of that particular geological formation. And if we introduce all these or the maximum of these in a particular policy framing, then we have to ensure the a strict follow-up of this to come some conclusion of it. So this is the main idea of showing this is to introduce you all to the dynamics of the groundwater system and what are the different complexities which are involved in this. Now we'll be talking about the systematic systems approach. Like I have already mentioned that it's a groundwater system is very complex, as you've seen in previous slides. So it's represent a very complex and a complicated system, which is not easy to understand in the complex hydrological condition, because it does not react only to the internal changes, but also the excitation from the outside environment. For example, in an aquifer, if there is any change in the soil properties, soil moisture, or anything else, it will affect the water. But there is an external excitation in terms of pumping. If we are pumping the water from an aquifer, it will definitely alter the thing. So it's a combination of both, and we have to try to identify and we have to understand the system. To understand this, there are two different scenarios. The first is the stochastic models. And in stochastic models, there are random properties. For example, it's a black box model, and there are random properties like distribution of the Young's modulus. Maybe when we design the dams, we have to identify the wind load, the earthquake, the vibration from different amplitude, and the displacement. So it's probably very incompatible with the conventional measurement technologies which are available today. For example, the UAVs, we have unmanned vehicles, we have different radars and this lidar surveys. So stochastic modeling data is sometimes very much complex, and standard field data is often too much limited to provide the geostatistical parameters needed for this modeling. It requires so many of numerical theories and computational impractical outcomes, and very unrealistic in large sizes. So generally we don't go for this, and we move for the deterministic model. In this, the material properties are well known. For example, none of them will be random, and the loads or the stress which we are applying will be deterministic. For example, if we are introducing the pumping, we know the pumping rate, we know the working hours of the pump, we know the capacity and how it's going to work. So a deterministic model is developed applying first the principle of the equations, and that means we are introducing the mass balance, energy balance, kinetic rates, and the physiochemical parameters, and so on. And it is called a white box model because we have all the known parameters in this. So there is a third approach as well. It's a hybrid model, as the name suggests. It's a mixture of both deterministic and the stochastic approaches. But the thing is that in hybrid model itself, when you are introducing the stochastic approach, there is a presence of a single random variable in the model, which necessitates us to consider it as a stochastic treatment. So that's the limit of this. So now I'm going to the challenges. I'll like we all are aware about the groundwater problem in different regions, specific in the South Asian and being more specific in the India. So I'll be not taking much time in this slides. So I'll be talking brief about the different perspective of this political and administrative boundaries. Like, in my opinion, I feel that the groundwater management is more based in our Indian scenarios on the political and the administrative boundaries, since water is a matter of state, and we are not that much concerned about forcing the people how they should say. And Delhi, the capital of India itself, is a classic example of this. Like, you can go through the news, and you can find there's so many disputes with the Haryana, Punjab, and like getting water from this upper Ganga Canal from the UK. So this approach may be faulty as the flow of water ignores the political boundaries. Therefore, the first challenge for effective groundwater management is to advocate the importance of the managing groundwater at the catchment or the river basin scale. And database on the groundwater system are either poorly maintained and or they are not available sometimes. And hence the second challenge to improve and share the basic data and generate and transfer the scientific knowledge. This is the second challenge, which I think it is there. In many parts of the region of the aquifer system, it is not well understood. And there is also a concern of the quality. So I think the third challenge is the quality of the data which is available there. A nationwide program of the regular water level and the water quality monitoring of the stress water system is there, but sometimes there are limited number of data sets, limited number of sites, or sometimes there is an error in measurement, or sometimes the instruments are not working, and also the like their distribution of different mechanisms or the machines to measure these is very like haphazard. In some areas, the concentration of the measuring devices is much, but in some other areas, it's very much nil. And we assume it to be representative of the whole area. For example, there are some areas where a single gauge is taking care of radius of 10 kilometers. While when we see practically, it's not the possible or the practical case in terms of the hydrological distribution of the groundwater resource, because changes in the aquifer parameters or the aquifer storage or its behavior with the groundwater or the interaction with the surface water can vary within the area. So we need to check the quality of the aspect. And therefore, developing a framework of monitoring of the groundwater level quality is the fourth challenge for effective groundwater management. And the fifth challenge is to evolve an effective legal and institutional framework for groundwater governance, which would include all the well-defined rights, water pricing, and the energy pricing. For example, if you look at the Delhi, the water is free for up to some limits, and after that, there is a pricing. But at the same time, there are people who are willing to pay, and they are free to use the water as and when they want and the way they want. For example, DJB is claiming that you need to treat the water for drinking purpose, but at the same time, people are using that water for washing their cars, because they know if a single person is living in a home and he's getting 200 liters of water daily and he's unable to use this, he's going to waste it anyway. So we need to be very careful about water pricing and the different tariffs which we are giving to the public, and we have to ensure the effective and efficient use of it. The sixth and the final challenge is to train a group of hydrologists or the social workers or the ecological hydrologists, those who are working in the field, and who will have capacity to comprehend a sustainable system that combines not only technical, but also the financial, social, and the environmental aspect and their impact. For example, if you can see, there is a debate on the news channels and among the different experts that the water quality of different rivers and the water bodies has enhanced during the lockdown. We agree with this. Yeah, but the thing is that we need to identify the major reason behind it. It's not like that all the pollution is being contributed by the industries only. For example, if you look at the classic example again of the Delhi, because we are residing here, so I'm giving example of Delhi only. There is an example of Yamuna, a small stretch of 22 kilometers passes through Delhi, but it gets around 70% of its pollution from Delhi itself. So from the upstream, there is a release of water to maintain the general ecosystem of the river, which has also enhanced the water, apart from the human intervention. So there are different aspects and different reasons behind this. And next time coming to the data, we all know there is a short period of record with the groundwater level trends and the limited monitoring we had, which I have already mentioned. And there are technical questions about the data quality. For example, monitoring a dug well that may subject to heavy use. For example, if you are taking sample in the morning and there is a peak use, people are using that. maybe after a few hours, it will regain the water level. And again, a dug well which is being continuously used is a question of technical quality of the data. And apart from this, there are non-technical factors which affect the data quality. For example, pressures to modify the data to influence the allocation of funds. For some reasons, we have limited fund and political interference which affect the data quality because they have to report it in some way. And also there is insufficient monitoring to capture the regional and the seasonal variation throughout the India I'm talking. The researchers who are working on their different models and all these things, they might be aware with this. So now I'm coming to the model development. How do we proceed for this? How we introduce all these things in our modeling? So first of all, when we start with the modeling, we have to look after what our objective is, because objective will in turn decide how much effort we need to put, what kind of output we want, and at what scale we are going to have the data, and how much complexity it is meant to involve in this. So very first thing is to identify the objective of your work, and then we have to proceed further. We have to find the geologic information from the field, and we have to find, for example, the which I have mentioned is the boardwalks of the different geophysics and the geophysical maps, which are now available with the Survey of India, and the Geological Survey of India sheets are there. Few are available on the open source, few are available in the published literature already. So using all this data, we can have a geological framework, we can have a fence diagram. And the other aspect is the hydrologic field observations. These are the challenging parts, like I have talked in the data part. So for example, groundwater hydrographs, pumping tests in the groundwater chemistry, groundwater level, the different types of well distribution of the wells, monitoring the data quality analysis, availability, and the number of parameters, number of their frequency of monitoring, and the missing values, the misinterpreted results. So many things we need to analyze before we give the input to the system. And using all these analysis and the data, we can prepare a hydrologic framework. Now, when we come to the second stage, we combine both the geologic framework and the hydrologic framework. Combining these two, and we give it as an input to the hydrologic conceptual model. They are conceptual models and also the numerical models. This is a journal model, conceptual model. What we do, we need to have some data on the pumping, and we need to have data about the hydraulic conductivity, storage coefficient, aquifer thickness. This is the minimum data requirement which should be there. We have the data of the stream, the rainfall, the temperature, the geologic formation, the different, the depth of the bedrocks and all these things. And we need to have the detailed design of the, not design, but the parameters of the wells which are there. For example, there is screen size, their running hours, their total withdrawal and stress, and a long historical record for few years for the calibration, the validation. And also we need to have K1, K2, and K3, which is hydraulic conductivity at different layer, and also in the different direction, because it will change with the direction as well. Once we have all these, we give them input in the modeling domain. Now, the question is, when we transfer the real world phenomena to the digital system, this approach is called preparing a model through some scientific approach, equations and concepts. So how do we define all these things in a system? There are different terms like boundary condition. So what it does is it gives a bound to the number of cells. We divide the whole area in the small packets, like I mentioned in the starting slide, and then it solves the general water balance equation for each cell. And in the end, it combines the results and gives us overall response. So in between, we need to define all these parameters as input. So I'll give an example of the groundwater modeling and the sensitivity analysis of the groundwater level prediction in Indo-Gangetic alluvial plains. So In this study, we have performed it for the UP East, and we have covered 5 districts, and it's a confluence of 2 rivers, like you can see in this figure. There is one figure, Gomti, one river in Gomti. On the other side, it's Rai River, and this is an interflow region between 2 rivers, and there are 5 different districts in this, and the area is 8287.50 kilometers square. And we had this like a project under the DST SERB, the Government of India, in around 2019. So to define these 2, in this figure, you can see there are blue cells. We have divided you can see the last figure, the green one. And this is the same figure in which we have divided the whole area into small grids. The size of the grid again depends upon your objective first, and second, the availability of the data. So once we define these cells, next we have to define the boundary condition. So there are different boundary conditions for different things. Like, for example, for wells, we have a well boundary condition, and in that also we have observation wells and the monitoring wells, and pumping wells are there. So for the river, I have chosen 2 because in this figure you can see there is a Gomti River, there is a Sai River on the either side. So these cells in blue, they represent the different rivers, and there are few cells, if you remember, on the top where the Barabanki and Raebareli is written. So these cells they are in green because they are not bound by either of rivers. So it's a general head boundary. There are different type of boundary conditions, and which you can go through. The standard literatures are available on different models. And I have chosen this general head boundary to restrict the flow. We are assuming that there is no flow coming from this direction. There is no flow going from this direction to the either direction. So the flow is restricted within this boundary. Next, we have given the input of the different parameters which are shown here, like hydraulic conductivity, storage coefficient, and the aquifer of the layer. This is a single layer system, but the more the information you have, the more the number of layers you can have, but it will increase the requirement of the computational resources, storage, and the runtime, and also the data. Once the model is simulated, we have, before coming to this slide, there are 3 different stages, rather, I should say, in the modeling. First is the calibration, means you are giving some input to the model and you are making it to understand that how the real world system is and how the model is behaving. And we give input, we keep 20% of it reserve, the groundwater level data. Whatever output we are getting from the model, we'll compare that output with the reserve data set, and we'll try to see how close it is. There are so many statistical parameters to see that, but generally we go for R square, coefficient of determination, and correlation coefficient, N is there, P bias is there. There are so many of them, but R square is generally used in this. So you can try to find out what's the relation between these 2. The closer it is, R square is to 1, better the value is. But it is not depending on a single parameter, as I have already mentioned. So, sorry. So we have to check the input parameters, for example, sensitivity of the model with respect to hydraulic conductivity, porosities, transmittivity, that is K into B, and also the inputs of the model distribution of the wells. And once we have calibrated, then we are ready to validate this. And this is the slide where you can see the calculated head by the model are in orange, while the blue is the observed head. When we compare these 2, the correlation coefficient is 0.98. That means it's fairly good to move ahead with this. There are different ranges for this. If, for example, if it is between 0.5 and 0.65, it's fair. Then we have 0.65 to 7, 7 to 0.75, 0.75 to 8, and likewise. So satisfactory, good, very good. Likewise, there are different categories. So it's a 0.98, so we can proceed further. Next is, we have trained the model. We know its behavior. We know the reliability of the model because we have calibrated and validated it. Next is how our system is going to behave in future. So we have to do a broad risk assessment for this. Since the model is calibrated and well validated, it's a good idea to move ahead with this. So there are different possibilities, but we assumed only two. One is the constant recharge and increase in abstraction rate. Means whatever the ground recharge is there, this will be there in the future also. But the population will increase and the abstraction rate will also increase. So in other scenario, we consider that there is a reduced to recharge and increase in abstraction rate. It's again opposite to the first one. That means if the population is increasing, the porous area will reduce and the infiltration of the rainfall in the ground will also reduce. In addition, if the population is increasing, there will be more demand. So they'll be depending on the groundwater. They'll be extracting more. That means there is a reduction in the recharge and increase in the abstraction, that is withdrawal rate. So in the first scenario, the current water rate was increased by the 20% based on the population changes during 2014 to 18. The initial recharge was kept constant throughout the prediction period. And we found that the areas on the top, on the right hand side top, if you can see, these are the areas, they have fluctuation between 8.76 to 8.85. And for the base period, the average was around 7.43. So there is a difference of almost 1 meter in that region, although the area is on the edge of a river, but there is a decline of 1 meter per year. In the scenario 2, where there is a decrease in recharge, we have a combined effect of both. We are assuming that the rainfall will reduce, but the total recharge to the ground will reduce by, and also there is an increase in the demand and increase in the withdrawal by 20%. All these percentages are fixed based on the trend of the population, how the population trend has changed, whether increased or decreased. There is some coefficient, and then we'll try to find out this. This are not a random value, like, and then again we have seen that there is an effect on the rightmost time. So it also showed a drawdown of almost 1 meter. So this is a basic idea how you can transfer your real world system into the digital system, how to introduce the different stresses in this, and how to check their response to this particular area. This can be performed, or this methodology can be adopted in any region with the similar geological or the climate condition. So when we talk about this, the hydrological situation, specifically in the South Asia, it reveals that there are several alarming trends over exploitation of the groundwater, causing long-term decline of the groundwater level. In regress of this, there is a seawater intrusion, which I have not mentioned here, because in this region, we don't have that problem. But in the coastal region, it's a major problem. So seawater intrusion and seawater intrusion and the deterioration of the water quality is another parameter which is there. And this calls a new institutional framework for the groundwater management. There should be a clear shift from focusing on the unsustainable exploitation of this groundwater resource toward an approach which is centered on providing the incentives to the different stakeholders for the better and more equitable management of this water resource. For example, if you see, there used to be some provision in the North India for this canal and all these things. Government was charging from the farmers, but later they found that the maintenance is not that much easy, and there were so many of disputes among the people using the canal water for their irrigation. So government tried to have some more idea, and they have given like subsidy on installing these tube wells in the area, subsidy on the electricity. So there are so many tube wells now in the irrigation field, and they're extracting the water like anything. And this has created stress for the groundwater, for the electricity, and also additional investment of money to maintain and to pay the bills for the government. So we need to have a better management, and we have to think about the equitable as well, because when we talk about the sustainable development goals, Then we have to be equitable. SDGs are there. SDG 6, which deals with the water, 6.4.1 talks about the equitable distribution, proper governance as well. So a fine-tuned combination of top and down and bottom to up approaches are also required. So with this, I suggest all the researchers to look at this word cloud which I have mentioned here. There are different fields for the research in the water sector, you can work on the hydrogeology, surface hydrology is there. There's a groundwater concentration of the pollutants, aquifer analysis is there. We can prioritize the area for the monitoring and the modeling. We can go for agricultural water demand, agricultural pollution, which is returning back to the groundwater system. And we have land use planning. We have soil change procedures for the increasing the fertility of it. We have aquifer management, we can have flow management, we can use remote sensing, we can control the supply. There is a intrusion from the pharmaceutical field for the chemical pollution. There is a different composition of the groundwater in the different areas. For example, there is industrial, there is a e-waste is there, there is a general waste, there is a solid waste, leachate is there. So effect of the arsenic in the West Bengal and the Bihar and this Dhanbad regions, you can see there is a difference in the soil moisture. Tensiometers are there to test it, but we need to have exclusive approach to find out all these things. We can have runoff modeling, which is also known as flood modeling. For example, in Delhi or in any other region, if there is a rainfall, the traffic is heavily disturbed. So there is a scope for this also. There are sensors, there are remote sensing approaches, there is a GIS. There are so many things to do with the groundwater. And we, the humans, are over ambitious sometimes, and we have literally destroyed this vital resource. So the climate and the groundwater both have already started responding. Now it's time for we, the humans, to respond. And it's a question that when we will start responding to this. With this thought, I hand over the session to Professor Singh. And thank you all again for listening to this. And I hope this will be giving some idea about what groundwater is, how it works, how the interaction happens, how we define the each, how we have different interaction between different parameters, how they're important to us, what are the different research fields, and how we can contribute. This is not, my idea was not to give a expert high level idea that this is going, this is not going, this is what we have done, this is what we have achieved. But I just wanted to provoke your thoughts about the groundwater, give a initial idea how you can initiate your research work, how you can incorporate different things in your research work, and how you can join hands for the betterment of the environment. Thank you, Professor Singh. Over to you.
Thank you, sir. Thank you for this wonderful session. I would request to all the participants, if there is any question or any queries, you may ask or you may post it in the chat box. If there is any question, you may want to ask. Yes, Kalpana Kapoor. You can unmute yourself and ask the question, or you can put it in the chat box. Okay. Yeah, unmute yourself and ask.
Is a better to way type in chat box.
Okay, someone, Professor Basir Ahmed, me too, everyone.
Yeah, Bashir.
Okay,
Bashir, I have seen your message, and I hope this depends on the organizers whether they'll be able to share this PPT or the recording. So I think you can contact.
Okay, after this whole FTP will end, we'll look into it, whether we'll share the recording. You can get the recording from our official YouTube channel, Vaageswari College of Engineering, Karimnagar. You can go to that YouTube channel. After this FDP will end, we'll have the recording uploaded into that. Okay?
I will send the feedback link in chat box. Everyone fill.
someone Shrikant asked, sir, what are the
I'll
sources of data of groundwater modeling?
Okay, so for the groundwater modeling, you can start with the Soil Survey of India. I'll suggest you first, and the Geological Survey of India is there. So you can collect the data for your geology of the area. Then you can contact CGWB if they have wells in that area. You can have the data of the well. Then you need to have data on your hydraulic conductivity and all these parameters. And also the boundary conditions should be known to you. So it depends on your experience and the skill of the data handling. So, but these are the minimum data requirement for this. How to increase groundwater in case of hard rock soil? Yeah. So in case of that, it's a unconfined aquifer, and there'll be no scope for that. But in the meantime, you can go for the some artificial wells are there, or you can have some granular mechanism for this. Yeah. Suggest Pragya Tiwari is this statistical mathematical model to forecast the quality of groundwater located near a waste stream. So I'll suggest you, Pragya Tiwari, to go for this Qual 2K. It's an open source, and you can predict the behavior of the groundwater contaminant. And what are the latest methods to improve the groundwater table? There are so many methods to improve this. The basic and which is more adaptable is rainwater harvesting and the artificial recharge of the wells. Apart from this, there is interbasin transfer and the more permeable beds of the rivers and the canals that have been designed nowadays. Yeah. What is the accurate method from Shrikant? What is the accurate method to evaluate infiltration capacity of soil at present? It depends upon your objective, like I have mentioned, but for the short term, there is a tensiometer, which is cost you around few lakhs of rupees. You can have that, and you can have the data of the soil. Is pumping rate available? Yeah, sometimes it is available. Yeah. And any other question, please?
Sehbaz Sheikh
The
asked, is
software
any
for river
software?
modeling.
Yeah.
So there are so many softwares for river basin modeling. It depends upon your what kind of modeling you want. For example, flood modeling, you can use Swim, or PC Swim is there, which is a paid version. And again, there is ArcSwat, there is ArcHydro, there is Haycrass, and there is a ModeFlow, obviously. GMS is there. So many modeling approaches are there, so you can use any of them. Yeah. Any other question, please? How do you find groundwater level? So vacant, you can contact CGWB. They have the data of all this, and few data is available in the open source and the different statistical book of your local region, which may be available with the irrigation department or the PWD of that area. Yeah. Next. Yes, Dr. Ranjan Mishra, he has raised, and can we use artificial intelligence to find the groundwater level? Yes, you can, because we have the mechanism of the different sensors which are already installed in the monitoring wells. CGWB is also doing that in few sites, and which transfers the data from that particular region to the particular site to the clouds, and we can transfer this information to our ANN and fuzzy, and then we can have modeling for the future behavior of this particular system. Yeah. Naga Shada, PPT can be shared by the organizers. Please, you can contact them. It's a question from Mr. Pradeep. What kind of career we will have if we choose groundwater engineering? It depends on at what scale you have personal interest in groundwater engineering. For example, if you go for PhD, you can go for R&D. You can have your own consultancy. You can associate with the different pollution control boards, and the monitoring boards are there. And if you have very good knowledge of the computing skill and programming, also you can design some code. You can develop some own software or algorithm. You can improve the existing, or you can develop as well. So there is a wide scope for all the engineering. It's not limited to the groundwater engineering only. There is a question from Vacant, sir. How do we find the groundwater level? Can we use satellite map? Yes, you can use satellite map. There is data called GRAC, GRACE. GRACE data you can use. Yeah. How do I estimate sediment for ungazed stations? Dr. P. Sundar, he is looking for estimate of sediment for ungazed stations. So for ungazed site, you can use different like Oxford is there. You can use Oxford, and it will give a output in form of sediment load. Yeah. Any other questions, please?
Actually, there are some questions like related to issue of Chennai water scarcity. What is measure need to do for overcome from this water scarcity? This question is asked from by Rupak Banik. He
Which one?
want to Rupak Banik, like related to the issues of Chennai water scarcity.
Okay. So before that, there is a one more question from what would your interlinking program would groundwater recharge apart from irrigation?
Okay.
And they are running very fast, so it's get overcome. Can you paste? I request Professor Singh to please paste them here. The questions. There are so many comments, so it gets before I
Yeah,
respond.
it's okay. I'll read it for you one by one. Wait. All right, very informative. Okay. And what kind of impact does interlinking of Indian rivers has on groundwater recharges?
So interlinking of the rivers will affect the it will not certainly affect the groundwater directly, but if you look at the local groundwater at a small scale, for example, if you are carrying water through some concrete canal from one place to other, you can have some mechanism or some reserve of water, say 10 to 5% of that particular water which is being carried out. You can recharge the well artificially instead of having some blank aquifer system is there. So it can be used for the artificial recharge. There is no other contribution because the interlinking itself will be on the concrete paved canals. So yeah.
There are so many questions about which are directly or indirectly linked with the water level, how to increase the water level. Like some most of the participants have asked this directly or indirectly. So some measure to increase the water level they are asking.
So groundwater level, like when we talk about increasing the groundwater level, we have a very simple thinking in our mind that we'll go for rainwater harvesting, we will dug some well or some pit, store the water, and it will go to groundwater. But still, the groundwater is not developing in that reason. The reason is that it's not like that you dig the pit and the water will go to the ground, but there could be different formation, like I have mentioned in the very first thing. After your objective, you need to identify the geological formation of that particular area, and there should be some technical approach uh, to have such pits or such stored water which have capacity to transfer the this stored water to the ground. This is the first thing. And also, second thing is whatever water is there in the ground, we need to maintain its quality. That means we need to reduce the chemical interaction with this. And also, third thing is the management. Like you need, for example, there is a solid waste unit, or there is a uh, and which there is a mechanism for storing the solid waste, but it is not covered or paved from the bottom. So they interacting with the groundwater, which will totally destroy this water quality. So this is the third thing. Fourth is don't withdraw unnecessarily the water, and you have to wash them in a smarter way and use it wisely. the more recycle, the more reduce uses, and more you use the recycled water, it will be reducing the stress on the surface and the groundwater both. So there are so many approaches for improving the groundwater apart from the technical research. Technical research will just give you an idea how the groundwater is behaving. It is not going to increase your groundwater level. The thing is that how you act is directly going to affect this availability of groundwater. Next, please.
Next question is about Chennai water scarcity. So I think these measures can be taken for the Chennai water scarcity as well.
Yeah,
Yeah,
these are very general.
these are very general. In Chennai, I think there is some problem of seawater intrusion as well.
Seawater is there, but in 19, if you see that they have declared day zero as well. So I think there was no water left in the rivers. But there are 4 different reservoir systems which are supplying water to the city, and they have. So now it's time to look at the reservoir system, whether their capacity was reduced, whether the load was more, whether there was ineffective policy or the ineffective governance or the ineffective cooperation from the public as well. It's not a general thing to depending on the uses. Obviously, it's part of it, but we have to look at the reservoir capacity as well. We have to look at the sedimentation aspect, and we have to look at reduction in its capacity to hold the water within the time. So there are so many aspects which are to be questioned. For example, this similar thing happened when there was a Sardar Sarovar Dam in Gujarat. When it was under construction, and there was a problem of the sedimentation in the initial stage, and the forcing on the main gate was not built in a single stage; it was built in many parts. So it increased the load of the water on the top of it. So it was about to it was taught by Professor V. Jyoti Prakash from IIT Bombay, one of the PhD students has resolved the problem in his PhD thesis. So there are so many aspects to solve this water scarcity in general. Yeah.
One good question is there, sir. At my area, all groundwater are polluted by soap factory. Any method to improve groundwater of my area?
Mm-hmm.
Yeah. This question is by Ashish Bhargava.
Uh-huh.
For the groundwater quality, like groundwater quality is affected by soap factories. So he wants to know any method to improve the groundwater quality of that area.
Soap affected. That means you have to first identify that what kind of mechanism they have before they discharge the water to the system, and whether their ETPs are working up to the mark or not, because there are guidelines for this,
Yeah,
and we have to
actually.
ensure whether they are following that or not. A second thing, you have to find out the different chemicals which are involved in this. Then again, you have to go for modeling, and then you have to have data. You have to have the original status of that system so that you can calibrate it in a good way. Once you are done with, then you have to identify the different pollutants which are involved, means chemicals which are involved in processing of this particular soap. And then among these, you cannot introduce all at the same time, but you can identify 1 or 2 most potential in them, and then you can introduce their product, and you can see the end result, and you can submit it to the responsible person for this policy making or the company that no, you are not doing it in a good way, and we need to work on it. So that's the only way.
Okay, one question is from Shrikant. Can QSWAT mod software be used for groundwater recharge modeling?
Sorry, I could not hear you. Yeah.
Sorry. One question is from Shrikant. He asked that can QSWAT mod software be used for groundwater recharge modeling?
Yeah, it can be, because if you are looking at the sweat and the mode flow, there is a combination of these two. There is a separate mechanism also. You can compute the recharge to the sweat, and then you can introduce it as a recharge to the or input to the groundwater modeling. Hello, am I audible?
Yeah, you are.
Yeah. So you can combine these two, and then you can combine these two, and you can come to the effect of the groundwater recharge on the groundwater modeling, like I have seen in my case study as well. So what I have done, I have computed the recharge from the sweat itself, and then I have given it as an input to the groundwater model to access the effect of this. That's why I have reduced the recharge rate by 20%, if you remember in scenario 1 and 2. Yeah.
Okay, all right, sir. And one more question from HP. I don't know what's name. Okay,
Nandita,
what
what is
have
the difference between mode flow 6 or 5? Mode flow 6 or 5, these are just the different versions. Sometimes they are improving the things. And I think you should go through their website and they'll explain this much better.
yeah?
Yeah.
So we got a lot of comments like this is a wonderful session. And one more question: how to determine fresh water and seawater interface for water quality?
So again, you have to go for modeling. That's the only solution because you cannot visualize the interaction of the surface and the groundwater, and also the seawater intrusion modeling. There are different software for this, and you can look at the different mechanism and the different concentration of the groundwater which is already there, and the force which they are interacting. So I think there is a modeling is the only approach.
Okay, one more question: where can we get data of geological formation of a study area?
Geological Survey of India is there.
Yeah, I think you answered it before. I also
Yeah,
someone asked similar question.
yeah.
Mm,
For the seawater intrusion, I would like to add one. There is a one software. I don't remember it exactly, but there is a get flows is there, so that can simulate the density dependent flow and which occurs in the coastal and the surface region, subsurface region of this. So this is a seamless water, surface water and like freshwater interaction is there. So this can discretize the same area into small blocks, and then it's like different land parcels and the sea also. So based on the parcels, it will see how the soil particles are interacting and responding to the particular contaminant in that particular region. So that is a good approach for this. Yeah.
okay. So we try to cover most of the questions. There are some kind of similar questions, so we skip those questions.
I'll suggest you to kindly look at the questions once, and you can
Okay,
compile them in a single file, and we can send the response to the all of them once the course is over.
okay. There's one initial question: what are the methods to control water pollution?
See, when you go for modeling, I'm talking about, then you have permeable reactor flow barriers are there, PRBs. There are so many literature available on this. This is the third stage after flow and the contaminant transport. So you can use that. There are no such exclusive studies in Indian scenarios.
Okay. So we try to like look into most of the question. If some questions are left, we'll surely try to answer it. Okay. So there
Yeah.
is feedback link in the chat box. You all of you participants go through this feedback link and fill it. It will be used for the attendance part as well. Okay. And once again, thank you, Dr. Shukla, for this wonderful session. We got a lot of replies from the participants as well. Like you have gone through this wonderful session. Thank you. Thank you once again, sir.